section 14.6, the last one in chapter 14, and we're going to talk about how catalysts work. So we already know that a catalyst is some substance which speeds up a reaction without being consumed as a reactant. How does that really work? It all comes down to the reaction mechanism. So a catalyst is something that will provide some sort of alternative pathway that has maybe more steps, but most importantly, its steps are quicker overall. So let's look at figure 14.21. It shows an example of a reaction that has some uncatalyzed pathway with a large activation energy barrier. And when you introduce a catalyst, that opens up some new mechanism that wasn't available before, that has lower activation energy barriers and is therefore able to proceed more rapidly. And I like to use the example of traveling. Let's say traveling from Cedar City to New York City. If you don't have access to an airplane, then it's going to take a certain amount of time. You're going to have to drive on the freeway, and it's going to take you several days, and there's just no getting around it. But once you have access to an airplane, then you can do a whole new journey. Maybe you go first to the south, to Las Vegas, in order to go to the airport and get on your airplane. And maybe you come into, I don't know where the airports in New York are, but maybe you land somewhere that's a little bit further from your destination than you would like. But overall, the reaction is, or the journey is much quicker because the airplane travels so much faster than a car. Okay, and this analogy works really great because it also answers another question. Sometimes someone will ask, well, what if a catalyst makes another pathway but it's not faster? Is it still a catalyst? And the answer is no. By definition, the catalyst needs to increase the rate of reaction. If I add new substances to a reaction, perhaps it will open up new pathways, new ways for this reaction to proceed via new reaction mechanisms. But if they aren't any faster, then the reaction will naturally go the quickest way that it can. And using our Cedar City to New York analogy, of course there are 100 ways that I could get from Cedar City to New York. I could walk, I could bike, I could drive the scenic route instead of the freeway. There are lots of ways that I could get from Cedar City to New York. But for the important question of how quickly can I get there, none of them matter except for using the car, or if I have access to an airplane, using the plane. The fastest one always wins. Molecules and chemicals are not sentimental. They're not going to take the scenic route just because they like seeing all the kitschy tourist traps. Instead, they're going to proceed in the most rapid way they can. And I guess the reality is they'll do all of them simultaneously. It's just because the one path is so much faster, that's the way most of them will proceed. Because molecules aren't sentimental, they don't have thoughts, they don't make decisions, they just go the way that natural forces compel them. Okay, so let's look at a reaction mechanism that includes catalysis. So here's a reaction, 2H2O2, that's hydrogen peroxide, and that's aqueous. Hydrogen peroxide will break down into 2H2O liquid plus O2 gas. And this happens naturally on its own. That's why hydrogen peroxide comes in brown bottles, because sunlight or any light will actually drive this reaction forward. However, it's very slow. That's why you can store hydrogen peroxide in a plastic bottle in the pharmacy shelf, and it'll still be good when the consumer comes to buy it. But it can be catalyzed to be very, very rapid by addition of hydrobromic acid. And so the catalyzed pathway goes like this. H2O2 aqueous plus 2 HBr. And now that I look at this, I guess this is an example of one of those very rare termolecular interactions. And the fact that it's aqueous instead of gas phase probably plays a part in how these three particles are able to come together at the same place in the same time. And that's going to yield Br2 plus 2H2O. And that Br2 is aqueous, not that it matters. So that's the first step, and that step is slow. And then the second step, the fast step, is Br2 aqueous plus H2O2 aqueous. That's going to generate the oxygen gas and 2HBr aqueous. And this one is fast. So do these add up to our overall reaction? Well, we'll have H2O2 plus 2HBr plus Br2 plus H2O2. That's everything on the left side. Everything on the right side is going to be Br2 plus 2H2O plus O2 plus 2HBr. That's everything on the right side. And if I cancel out my Br2, cancel out my 2HBr, I'm left with 2 hydrogen peroxides, yields 2 waters and an oxygen. That is the overall reaction. And what we see here is the presence of some intermediates. Br2, this is an intermediate. It is first generated and then consumed. But we also see a catalyst, HBr. HBr is a catalyst. And HBr is first consumed and then regenerated. And that's really the difference between an intermediate and a catalyst. The catalyst is first consumed and then regenerated. Well, let's analyze the kinetics of this reaction. So we would expect that the rate is going to equal K1 times H2O2 times HBr squared. And so here we see another feature of catalysts is that they will appear usually in that rate law. I should say usually. They don't necessarily always appear. There can be special circumstances where they don't. But they will usually appear in the rate law, and they are first consumed and then regenerated. And so if I want this reaction to go faster, I can add more HBr, and that will increase the rate. And HBr is consumed in the first step, but it's regenerated in the second step. So over the course of the reaction, my HBr concentration will actually be constant. And when the reaction is all over and there's no more hydrogen peroxide left, I will still have every last bit of hydrobromic acid that I started with. So that is catalysis. Now, catalysis can happen in a number of different ways. This was an example of an homogeneous catalyst, because the hydrobromic acid and the reactant were both aqueous. They were in the same phase. So there is a homogeneous catalysis, and then there is heterogeneous catalysis, where the catalyst is a different phase than the reactant. This is most often where you have a solid catalyst. And so a lot of precious metals like platinum or rhodium, are actually really useful catalysts in important chemical reactions. You may be aware that on modern cars there is an element that is placed in line with the exhaust pipe called a catalytic converter. And that catalytic converter actually has some precious metal inside of it. You can go get broken, clogged, old catalytic converters, and it's worth the time and money to extract those precious metals. Some people will do that, you know, to recycle those precious metals from old spent catalytic converters. And what the catalytic converter does is it takes unspent fuel and carbon monoxide, which are the result of imperfect combustion in the engine. Maybe there's not enough oxygen, the pressures aren't right. You're never going to get a complete perfect combustion reaction in your car's engine. Those things like unspent fuel and carbon monoxide are harmful to the environment. They're either literally toxic to humans, or they at least act as greenhouse gases. And so it would be nice if we can convert them into more benign things instead. So the catalytic converter here has these precious metals substrates, and as the carbon monoxide and the unspent fuel in the exhaust pass over those precious metals, they will actually undergo a reaction to form water and carbon dioxide, like a complete combustion reaction. It'll do that without a spark. There are no spark plugs in your catalytic converter. These precious metal catalysts are so effective and efficient that simply flowing your exhaust over them is gonna catalyze the reaction. And the way they work is that the gas particles, which are ordinarily in the gas phase, traveling every which way chaotically with large amounts of empty space between them. Well, when these gas particles encounter the rhodium substrate, they will stick to the surface. And when they stick to the surface now, they'll travel along that surface, and a three-dimensional space that they were inhabiting before has been reduced to a two-dimensional space. And the probabilities of them encountering one another are hugely magnified. And then furthermore, the fact that this surface is able to stabilize transition states, it's able to lower the activation energy barrier, is a second part, and that's what makes them really effective. They'll increase the rate of encounters by reducing everything down onto a two-dimensional surface, and then they will decrease the activation energy barrier by stabilizing the transition states. So that is heterogeneous catalysis. Heterogeneous catalysis is important in a lot of industrial applications. Catalytic converter, chemical plants that make all of the chemicals that are a part of the industrial chemistry industry, and homogeneous catalysts are really important biologically. So inside our bodies, there are all sorts of chemical reactions that are going on all the time. And most of those chemical reactions are sort of energetically disfavorable. They're very slow. They're not very likely to occur, and therefore we should be dead. The reason we're not dead is because our bodies make extensive use of specialized catalysts that will take these reactions and speed them up enough to maintain life. And those catalysts are called enzymes. And so the way the enzymes work, or at least many of them work, is it's a large biomolecule. It's composed of proteins, and it has regions with positive charge and negative charge, regions capable of hydrogen bonding, regions that are nonpolar. And all of those different regions are held in three-dimensional space in a very precise way by the structure of the protein that makes up the enzyme. And what they make is a perfect, so the reactant that they are trying to catalyze the reaction of also has regions that are maybe positively polarized and negatively polarized and capable or incapable of hydrogen bonding. So the enzyme is designed and structured to match and mate with that substrate. It's the perfect shape so that the substrate will it will dock into that enzyme, and then the enzyme will stabilize the transition state. It will maybe grab other cofactors, other molecules that are involved in the reaction in a similar way to the original substrate. Enzymes will again reduce the sort of the volume that two reactants have to find each other, because it'll grab one of them and grab the other, and then sometimes it will physically push them together. There's a great diversity of particulars about how enzymes work, and some of them are really remarkable. But the bottom line is that they'll grab the substrate and catalyze the reaction, then it will release the products. Okay, so excuse me. So the enzymes will often stabilize the transition state by shifting electron density away from bonds that need to be broken, pushing electron density toward regions where bonds need to be formed and things like that. It's really quite remarkable. All right, so let's look at this reaction mechanism here. We can have propane, C3, actually this is propene, C3H6 aqueous plus H plus aqueous, forming C3H7 plus aqueous. And then we have C3H7 plus aqueous plus H2O liquid, and that's going to form C3H9O plus, C3H9O plus aqueous, and then C3H9O plus aqueous is going to form C3H8O plus H plus aqueous. Okay, so this is the proposed three-step mechanism. Can we identify any catalysts and intermediates, and what is the overall reaction? So let's do the overall reaction first, because that's going to help us identify catalysts and intermediates. On the left side we have C3H6, we have H plus, we have C3H7 plus, we have H2O, and finally we have C3H9O plus. On the product side, we're going to have C3H7 plus, C3H9O plus, C3H8O, and H plus. Sorry, that's a bit sloppy. There was a lot to write. So what can we eliminate? C3H7 plus. We can eliminate C3H9O plus. And we can eliminate H plus. So our overall reaction in the end is C3H6, the propene, plus H2O, the liquid water, is going to form C3H8O aqueous. That is the overall reaction. which means that C3H7 plus is an intermediate. It has been consumed first and produced second. C3H9O plus is also an intermediate. Produced first and then consumed later. Did I say that right for the first one? Produced first and then consumed later. And then finally we have H plus, which is consumed first and then regenerated later. That makes this a catalyst. Okay, and that's it for 14.6.